going to start talking first a little bit about motivation. Why do we want to talk about this? Why is this an interesting thing? And the focus on that is that over the last 20 years or so, or actually 30, 40 years, the rate of change of computing clock speeds has changed. And that has driven some things in the hardware industry of computers. And it's interesting to look at the evolution of PDF and overlaid on top of that change. And we'll look at, discuss briefly, what our user expectations are when viewing documents and how that affects the software that's used for that. And since we want to talk about doing accelerated rendering, mainly using parallel programming methods, I'm going to talk briefly about two open source projects, Ghostscript and MuPDF. The advantage of course, being open source is that it's straightforward for anyone to go ahead and grab this code base and play with it to do these types of implementations. And the three areas that kind of focus on is the use of multiple cores for rendering, the use of single instruction, multiple data hardware for acceleration, and then briefly discuss the use of general purpose graphics processing units for acceleration. So first, let's just talk about what kind of is driving this. So here on the this plot that I made of, so here on the x-axis we have year from about 1970 till today, and then on the y-axis we have clock speed here on a logarithmic scale. This is a plot of Intel microprocessor clock speeds. And so what you see is that this thing's definitely going up over time. And if we do a linear fit from back in 1970 when they kind of first introduced the microprocessors up till a little past year 2000, quite a rapid increase there in clock speed on CPUs. Of course, if you do a linear fit on the data since then, you can see that the rate of change here has slowed significantly. And it's kind of interesting to overlay the evolution of the PDF specification on the same plot. Here we're running from 1985 down there till today. PDF 1.0 came out around 1990. And you can see, I've kind of tried to overlay where things are. The biggest, to me, computational-wise, the most expensive thing that was added to the PDF specification over this time period would have been the introduction of transparency. Transparency is an expensive operation to deal with, and since that time, well, there hasn't been a whole lot of huge things that become expensive computationally with the PDF specification. It was interesting to hear the keynote, though, this morning, because he was kind of pushing that, that things need to become evolve even more with more things going on. So that would definitely push computational requirements for rendering or whatever. But what does this slower rate of increase in clock speeds mean? Well, years ago, I swear every year, I would get a new laptop just because a faster machine meant better performance. And people kind of expected that to continue, right? They expect to see faster loading, viewing, editing, printing of documents. I mean, it's just assumed it's always going to be improving. And it used to be, of course, with the faster clock speeds, as a software engineer, you could just use the same code you've always been using, and you'll get better performance. But now with things not getting faster, to get this user expectation of things improving, you've got to do some other things. And at the same time that this slower clock rate change has been occurring, or a slower rate of change in clock rates, there's been changes in the hardware in terms of the introduction of multiple cores in the CPUs, introduction of single instruction multiple data hardware, and then, of course, there's been this explosion of the use of GPGPUs. Of course, now, the problem is that software engineers got a lot of work to do because they've got to figure out how to take advantage of all of these things. and to go ahead and implement these as parallel programming problems and find the problems and get them to work on this hardware. To demonstrate some of that, I'm going to talk about a couple open source projects that are used to implement some of these things. One is Ghostscript. So Ghostscript you've probably heard of from way back when. It's a document conversion rendering engine. It's back from 1988. So it's originally developed for PostScript. Since then, it now handles PDF, PCL, XPS, all those as page description languages. It's written in C. It's an essential component of Linux printing pipeline. It has a dual license. So as I said, it's an open source project, and it has a AGPL version 3 license, and there's also a commercial license available for it. Ghostscript is really focused primarily towards printing applications, and towards that end, it has support for extreme color management and things of that nature, and it has a wide variety of output formats. So you can convert between these vector-based languages, and the source and all the documentation is available at ghostscript.com. A similar project is MuPDF, which is also open source. It's more of a toolkit, though, as well as an application for viewing PDF and converting them. And it's also an XPS interpreter. Its development started in 2003. It's written also in C. And its focus, unlike Ghostscript, which is focused mainly towards printing, it's focused more towards development of viewers. It supports annotations, form filling. You can do redactions of text and things of that nature. It actually has APIs for Java and JavaScript, so it's kind of useful towards that. It has the same kind of licensing as Ghostscript, and then its documentation and source are available at MuPDF.com. So, given that I've got these projects and one of the approaches to parallel programming is to take advantages of the multiple cores and SIMD hardware and GPGPU. Well, basically you have to look at the problem that you've got. Maybe it's dealing with transparency or doing color management or half toning, and somehow you've got to look at this and figure out how can I break this thing up. Is the operation I'm doing, is it made up of a series of tasks that are completely independent, that I can go ahead and do those in parallel, or do I need to look at both the data and the task? Is the data, perhaps I can operate on different chunks of the data, maybe individual rectangles or bands, and I can do those in parallel. Or is there a series of operations, perhaps, that the data is going through that I can go ahead and set up in a pipeline so that those operations can each happen in parallel, but on different chunks of data as it makes its way through the pipeline. And there's approach that's called a wavefront. For example, if I'm doing error diffusion on a page, you can think of this as going through the page and half toning it. There's a decomposition I can do on that. So we kind of have, again, we have the multiple cores, single instruction, multiple data, and GPGPUs. So let's talk about cores first. So I do a plot of again, this is for Intel, number of cores, timeline that occur in CPUs. You can see that right around the time that we saw the clock speeds kind of rate of change slow down, we see this increase in the number of cores that are getting occurring in the CPUs. So what can we do with that? Well, this is what's done in both Ghostscript and MuPDF to do that. So we basically have let's say we have a page a PDF page that needs to be rendered. This page is broken down, all the commands to do the drawings and the fills and the text placement, et cetera, is broken down into a display list. And this is basically a set of high-level commands that are stored in a very optimized manner. And what I can go ahead and do is render different bands of this page with different threads. So each of these threads would run on a different core on the CPU. When this particular thread is finished rendering its band right here, it'll then kick off and start rendering the next band. So I get this parallelism where these are getting rendered at the same time. With Ghostscript, we can also have the option where while these threads are rendering this particular page 25 here of the PDF specification, page 26 is actually can be interpreted and the display list being created by another thread. And then in addition, depending on the output device you're going to, you can add in certain operations that the threads will go ahead and continue to do, for example, object-based color management or half toning, and so these will all occur on separate threads, and so you're getting this parallelization. If I look at other print engines, now the advantage here, of course, on Ghostscript or MuPDF is that it's open source. I can look at the code, I can go ahead and go in there and hack away. The other print engines, Adobe, I have to kind of infer from the specifications, for example, they claim that they have this thing called multi-rip, which lets me run multiple instances of the rip, so I could do that on different threads. And they also state the specification that they have multi-threaded advantage rendering, so basically the same thing as MuPDF and Ghostscript have. Global graphics on the Harlequin rip, its specification says that it uses multiple threads for transparency, compositing, and rendering. And like I showed with Ghostscript, allows you to process the next page while rendering the current page. So that seems to be a common theme on the various PDF engines to take advantage of multiple cores. I can go ahead and do some interesting timing samples here using Ghostscript, where I had a Intel 24-core Xeon processor, had a clock speed of 1.6 to 2.67 gigahertz. I went ahead and forced the CPU to run at the slower clock speed when doing these timing tests because the Intel chips will do thermal throttling. Basically, if they start to get warm, they'll go ahead and turn down the clock speed. I didn't want that to affect my timing tests. I rendered out to CMYK color space, the whole page, with a ProGraph 53 ICC profile, defining the color space. So that's 32 bits per pixel, CMYK, at 1200 DPI resolution. The page is actually rendered out with what's called the null device, which means I'm not doing any disk accesses to write out the data, because I didn't want that to affect my timings. And basically I varied the number of threads from 1 to 24 while rendering. And I did 10 runs in each case and recorded the minimum time. The pages that I ran, one was the Altona 1.2 visual test page. It has, when Ghostscript renders this, it actually breaks the page down to 376 bands. And it's about 1.25 gigabytes of data rendered out to CMYK at 1200 DPI. The Altona 2.0 test page, Ghostscript breaks that down into about a little over 1,800 bands as it renders it. And then this page right here was just a series of images, all in sRGB color space, and Ghostscript breaks that down to 168 bands. So as we render, for example, the images file, this here on the x-axis is the number of threads, so we're going from 1 to 24, and it's the number of seconds to render the file. And you see it's kind of 1/n kind of curve that you would expect. For example, with just one thread, it takes 18 seconds to render that page. With two threads, it's somewhere around 11 or so seconds. And you see a similar kind of thing with the Altona text files. It's a funny little bump there. I'm not sure why that happens there, but it was consistent. Anyway, so that's the advantage, the performance boost that we end up getting when rendering out to multiple cores. So a nice improvement. So let's move on to the next topic, which is single instruction, multiple data operations. So the idea here is that there's basically these hardware methods in the Intel chips and also in the ARM chips that instead of being able to just add A plus B and getting that result, instead what I can do is pack, for example, here I've packed 8 numbers in this register and then 8 numbers in this register, and then with a single operation I can go ahead and add each of those up. So instead of just getting one addition per cycle, I end up getting 8 additions per cycle. The problem with this is that often it is getting the data organized properly. So you've got to load the registers and get the data in the proper way. And there's a whole series of operations you can do with shifting and adding and multiplying and various other operations. But the problem is getting the data organized and getting it back out. Sometimes that can negate the benefits that you're getting from the parallel operations. The SIMD stuff started to appear back in 1997 with Intel's MMX stuff. Since then, they've evolved to what they call SSE versions, and those have continued up until recently, where then they switched to AVX namings, and now with AVX 512, which works on 512-bit registers. Generally at work, I've done some stuff with AVX2, but generally work on the lower end chips that support SSE 4.2. There's also ARM SIMD operations, and now they currently call that Neon, and they have that for 64-bit processors. So you can see a lot of this development occurred, again, since this period of when clock speed started to slow down. So what can be done with SIMD? Well, there's lots of applications you can do. Image scaling, image rotation, half-toning, transparency blending, color conversion, CRC and MD5 computations, inflate, deflate. All these are great operations to happen or to take advantage of when processing a PDF documentation. Encryption, image encode, decode, for example, JPEG or JPX content, and obviously matrix operations. If I go out just to GitHub to see what people have done, there's all kinds of projects out there. People have done image scaling, general image processing library, both for Neon, SSE, and AVX. If you're a Java programmer, there's JSON parsing, matrix and vector operations, image codec for libJPEG, a deflation project, CRC project. I haven't actually looked at these. I just noted that there's lots of stuff out there. What's going on in other areas? I know I don't know exactly what Adobe's doing and how they're what they're doing with SIMD, but I do know that they obviously use it. I saw a job mentioned improve performance of Photoshop using multi-threaded SIMD and GPU techniques. Oh, okay, well, that's kind of right along the line of this talk. Lightroom uses SIMD for camera raw processing, I've read, and Photoshop's known to use SIMD, and I have no doubt that Acrobat uses it. Global Graphics likely using it, but I couldn't find anything on the website or in their literature claiming for it. So with Ghostscript, I've implemented some various image scalings, both nearest neighbor linear and Mitchell cubic interpolation, as well as doing some higher speed methods when you have to do just 2 or 4 or 8x types of things. Image rotation, half toning, mainly in matrix thresholding, half toning. Transparency blending, which is as I mentioned earlier, a very expensive operation. And then color conversion, in particular doing tetrahedral interpolation in color. So I look at what kind of improvement do I get over standard C implementations in this? Well, these are all scaled so that the standard C implementation is shown in blue here. And this is percentage improvement. So the SSE implementation, you're getting easily a 2x performance improvement. This is over a series of different files. If I zoom in on a particular file, of course, it depends on what the file is using, that particular operation, right? If I look at the image file we had earlier, this is going to go through lots of tetrahedral interpolation, do all the color conversions going from sRGB to CMYK, for example. Tetrahedral interpolation is a difficult one to implement because there's lots of decisions that need to be made to determine which tetrahedron you're actually in before you can do the interpolation. So you see that for this particular file, percent speed up is only, a little shy of 10% speed up using SSE implementation. If I look at the actual function that's doing the interpolation, that's actually almost 20% speed up. This particular file here, this page of this file, is actually a 14-page file. It's from the Apple's AirPrint performance testing. So if you want to have an AirPrint ready logo stamped on your printer, you need to have a certain performance level on these types of files. And this particular file has some transparency in it. And if we push that through with SSE, we get a 10% boost on this particular file. Now, it only has a little bit of transparency. If I actually look at the function that's doing the transparency blending, I get over 70%. I'm actually getting over a 70% speed up boost going through SSE. The difference being, the reason this has such a large boost is that transparency blending, there's nothing complicated in terms of making decisions and if-else statements that can be a headache for SIMD methods. Instead, everything's just basically brute force raw transparency compositing. So that's where we are with the SIMD. Let's talk about the general purpose GPU stuff. So actually it's kind of interesting because again, the same time period, around year 2000 that these GPU chips started to show up with NVIDIA, really defined the GPU around 1999. Prior to that, there were 3D graphics cards, of course. But the thing that really made this more of a general purpose thing is when in 2007, when NVIDIA introduced the CUDA development environment. And since that time, it's really opened up the use of these things for all kinds of operations other than used for graphics. So the difference, of course, is that with the CPU, I may have a few cores here. With the GPU, I may have thousands. This recent NVIDIA device that came out has over 4,000 shader processors on it. So I've got this tremendous processing power that is available to me. And this is on most desktop machines, and my laptop even has a NVIDIA GPU. Now, not to be outdone, of course, you gotta realize that today Intel they will pack into the CPU. They may have a GPU here that exists also. They would like to compete with NVIDIA, but generally that GPU doesn't quite have the power of one, if you have a dedicated GPU card. One of the problems, though, with using the GPU is that the difficulty is that you generally have the model looks like this, where you have the CPU, you have some system memory, and the GPU over here, and some GPU memory. You've got to get the data that you want to deal with out of the system memory and the GPU memory. GPU does its processing, you got to get it back out of the GPU memory into the system memory. There have been changes in that with NVIDIA, for example. There's a unified memory model now that there's this kind of shared memory between the two. But it does get rather complicated, and I'm not going to go into this in any kind of detail because it just gets a little overwhelming. But the thing that to note is that at the end of the day, that the hardware on the GPU kind of consists of these multi-processors, okay, these streaming multiprocessors. And the idea is that these things are kind of running the same small bit of code, okay, but they're running it on different pieces of data. And if they can run these things in parallel, at least the same code operations happening on different data, you kind of get this SIMD sort of thing going on. Now, one problem is, of course, if that bit of code has if-else statements, for example, then suddenly you've got conditions where this particular streaming multiprocessor is running a different bit of code than the other one, and you lose that parallelization. So what kinds of things can you do with these? Well, obviously graphics drawings. It's used heavily today in deep learning applications. That's really driven NVIDIA sales off the charts. If you go to GitHub, you can find lots of examples of CUDA implementations for various applications. As far as what I know is out there, I had read that Adobe Premiere Pro is using CUDA for video editing. Lightroom uses it for interactive image editing. I wanted to use it to see how things could happen. Again, I took the hardest problem I had, which is the tetrahedral color conversion. That was the GPU that I had, and the CPU. And the approach, this kind of a silly approach at first, was just to to go ahead and port the existing kind of C interpolation code right into the GPU. So I have this small snippet of code, and I basically built that for the GPU. Now, the difficulty, though, is that, again, as I mentioned, for GPU parallelism, is if I've got branching decisions, and that's what occurs here in the tetrahedral color conversion. And so, and also another issue is that the GPU has a fairly small memory, and Ghostscript tends to use very large multidimensional lookup tables when doing color conversion, size 49 and 49 and 49. And those do not fit in the GPU memory, so I had to go ahead and use a smaller size table. But in any event, if I look at the standard C implementation and I scale that to 100%, the SSE guy was running up here, and unfortunately my GPU implementation actually ran slower than the standard C. And a lot of that, again, is due to, well, one of the primary things is branching. The other thing that, the next steps actually is how can I fix this to make it go faster? Well, probably looking at using memory more efficiently, possibly reorganize the actual code, try and improve the parallelization. A big thing, though, is this right here. Right now, the way it's implemented is the CPU host says, OK, I'm ready for you to do the interpolation on this big chunk of data. Here you go. And then the GPU does its thing, and then it says, OK, here's the data back. So I'm doing this synchronously. What I really need to do is probably implement a pipeline and have the CPU host operating on some of the data while the GPU is doing its thing on the next data set. That's a little tricky to implement, and I didn't have enough time to do that before this presentation. The other thing is floating point usage. The GPUs are all native floating point, and I'm doing everything fixed point. I probably can get a little bit of speed up if I did that. And there's lots of nice problems that don't involve branching, like this problem that I have in MuPDF, transparency compositing. I did try linear color conversion instead. That would be quicker. Facial interpolation of doing enlargement or reduction of images and half toning would all be good things. Where's this all heading? Clock speeds, as long as we're doing hardware and silicon, the clock speeds aren't going to, the rate's not going to start increasing like it used to be. And so we're just going to end up having more processing units, and so it's going to put more burden on software engineers to make use of those things. It would be nice to have improved development tools. Things have come a long way since certainly the 90s, but there's room for improvement there. And I think finding, at least for me, it's digging up more parallel processing opportunities in rendering and converting documents. There's lots that can be done, I think, on the interpreter side, for example, and so that's it. So thank you, and I don't know if I have time for any questions or not.